All right, so we'll go ahead and get started with module 1.3. So we've had a little bit of introduction to how to use CompuCell, what's been done with CompuCell at module 1.1, and then Pedro just taught us all about the underlying algorithm that runs CompuCell simulations. And this exercise is going to be kind of a follow along to what he was doing. We're going to be looking at a cell sorting example, and you'll have a chance to actually build a model on your own this session. So as with everything else, this slide deck can be found in the student materials folder at the link on the lead slide here. And again, we'd like to thank our funding through the NSF, as well as our support through the IUB Biocomplexity Institute, as well as the OpenVT and Glimprint initiatives. Here we go. Yep. So today we're going to talk a little bit about the basics of how cell sorting can be represented computationally. Like I said, there'll be an opportunity here to get some hands-on experience with building a CompuCell3D simulation and modifying the code to kind of get the output that you are interested in. You'll become familiar with a variety of CompuCell code plugins throughout this, and of course for the rest of the week. And this will also give us a chance to explore how, excuse me, how various parameters affect simulation behavior. So when I talk about cell sorting, it's important to explain what we talk about. So cell sorting is a phenomenon that's observed during embryonic development in which randomly mixed aggregates of two cell types will tend to sort into groups of the same cell type until eventually one type of cell engulfs the other. So it completely surrounds the other. So there's a big blob of one cell type in the middle and then a sphere of the second cell type engulfing the central one. Through various experiments over time, people found that the mixtures of same pairs of cell types consistently put the same type of cells towards the center. So cells reliably engulf specific other types of cells. Obviously, this would be important during development. You always want specific types of cells to end up on the outside as versus the inside. But there's a sort of transitive property thing where if cell type A engulfs cell type B and cell type B engulfs cell type C, then cell type A will engulf cell type C. So there's a hierarchy of engulfment behavior during embryonic development. This is thought to be due to molecule types on the outsides of cells called cadherins. So these are molecules, transmembrane proteins specifically, that stick out of the membranes of each cell and then stick to each other. So it allows cells that come into contact to kind of stick using these cadherin bonds. Different types of cells have different types and amounts of cadherins in their membranes, and this is what creates the affinity that Pedro was talking about in the last session. So cadherins prefer to stick to cadherins of their own type. So if your cell type has a similar balance and number of cadherin types, they will tend to stick to each other versus to other cells with different amounts and distributions of cadherin types. Obviously, if any of you are familiar with molecular dynamics simulation, if we were to do this simulation in one-to-one detail with full cells with individual cadherin molecules sticking off, it would take a very, very long time. And general policy is that the modeler usually still likes to be alive by the time that their simulation finishes running. Doing this at the molecular level would be very computationally expensive and would take a very long time. So we have to make some assumptions about what kinds of things we can simplify to get the behaviors that we're looking for. Throughout the last 60 to 70 years of experimentation on cell sorting behavior, there's a number of different hypotheses that have been put forth. The one that we'll be looking at a computational version of today is Steinberg's differential adhesion hypothesis, which states a couple of things: that cell types have, like we talked about, this consistent hierarchy of adhesion energies per unit surface area when they come into contact with other cells. The cells adhesivity depends on the number and type of cell adhesion molecules in its membrane. So these are the cadherins. In our simulation, this is abstracted down into a scalar interface value. So we kind of take this idea of simplifying or abstracting out the cadherin molecules into a representation of this hierarchical adhesion energy per unit surface area idea. Those are kind of the two important points here. Obviously, there's a couple others. In the hypothesis, we assume that cells are fluctuating randomly within an aggregate, so there's no directed movement that's causing this cell sorting behavior. And cells don't grow or change their properties during sorting. And then less adhesive cell types engulf more adhesive cell types, which may make sense as we get a little bit further into the actual example here. If your cell type is more adhesive, it's going to want to form tight clumps as opposed to thin layers that engulf other cells. So this is what cell sorting simulation looks like in CompuCell. I have a short video here. You can see two different cell types, blue and green. Green is in the process of engulfing blue. This is the simulation that we'll be building here in just a moment. And you can see that as the green cells begin to connect with each other, they kind of continue to form into the engulfing membrane. All right, so let's take a slightly deeper look. And Pedro showed you a little bit of this in the last session, but now we're going to look at the example of two cell types. So let's build up to that. So again, first, if we're considering a single cell type in a medium, here we have yellow squares representing cells and mediums representing green. We have two contact energies, so like we talked about in the last session. So here we're actually, in Pedro's example, we were looking at pixels in a lattice representing a single cell and deciding whether or not the next pixel is going to be added to the cell. In this case, we're looking at actual cells distributed in a medium. So each yellow square here is an individual cell. Probably should have used a different color to avoid those schemas, but so suppose we have 8 cells. We have two contact energies, the contact energy between the cells and between the cell and medium. If they're arranged in a checkerboard, they each contact the medium on all 4 sides. So we have 4 interfaces between the medium on each cell. And we end up with total contact energy for the checkerboard pattern of, again, 4 interfaces per 8 cells times your energy value for your cell to medium interface. You have 32 times J cell medium. This would be the most possible contact area between the cells and the medium. In contrast, we have our compact arrangement. So again, cells and medium. Here we still have 2 contact energies just between the cells themselves and between the cell and the medium. If they're arranged in a compact square with a notch like this, they contact the medium as little as possible. So that's maximizing the amount of cell-to-cell contact and minimizing the amount of contact with the medium. In this case, we would have 12 times the energy for cell to medium because we have 12 medium to cell interfaces, and then 10 cell to cell interfaces. So this is like I said previously, the checkerboard, most contact with medium, compact, least contact with medium. All other configurations will have some energy value intermediate between these two. These are kind of the two extreme configurations that your system could take with a single cell type. And here we say if the energy of contact is greater than 0, the pattern will evolve from checkerboard to compact. And if the energy of contact is less than 0, then the pattern will evolve from compact to checkerboard. And you'll get a chance to experiment with this here in just a minute. So here, now we're looking at 2 kinds of cells. So we have 2 embryonic cell types in medium with specified contact energies per unit area between them. So in this case, we would have 5 energy values. We have cell type A to cell type A, cell type A to cell type B, cell type A to medium, cell B to B, and cell B to medium. So again, remember we have a contact energy value for each of the interfaces between objects in your simulation. So if we were to have 3 cell types, we would have an additional couple of energy values there because you would have cell type C touching A, C touching B, C touching C, and C touching medium. So key takeaway is we can represent the contact energy as an abstracted adhesivity value, sorry, it's a difficult word to say in the middle of a sentence, between each cell type. The system will try to arrange in a pattern that minimizes the total amount of contact energy. So we talked already about the energy minimization function that kind of drives CompuCell on the back end. It will try to find a configuration over the course of time in a simulation that minimizes the total amount of contact energy based on the values that we've assigned to each of those interfaces. So now let's talk about how to actually build this. So if you have CompuCell open, or if you closed it during the break, go ahead and reopen it now. And we're going to build a simulation that starts as a blob in the center with 2 cell types randomly distributed throughout the aggregate and have it sort into a system where one engulfs the other. So if you've got CompuCell open now, we got some instructions here. You've had a couple of chances to build models using the wizard today. So let's try for one more. So we have some instructions here. I will let people try this on their own for the next 5 to 10 minutes. And then if we need to, we can walk through it together. But the instructions here, once you've got it set up, you should have an image that looks like the figure on the left if you just step the simulation when you start it. So once you've got this figure on the left, go ahead and post an image of it or a screenshot of it in the chat. So the don'ts of file naming, that's a good question. I don't know if we went over that. The biggest thing is not to start your file with a number. So you should start your simulation name with an alpha character, not numeric. And you want to avoid spaces, hyphens, and periods in your file names. So try to stay, you can use underscores without any problem, but try to stick to all alphanumeric characters, except for the first character, which needs to be a standard letter. Yeah, just in general, avoid special characters, except for underscores. Underscores are fine. Where is the neighbor order? I don't see this in general properties. So neighbor order should be in your first, in the lattice specification page, the first page of the wizard. I think it's still the first page of the wizard. Yeah, it's in your first, after you name your simulation, Karen, it's in general simulation properties. It's called pixel copy range, and then in parentheses, it's got neighbor order there.
So one thing that I want to say is that people should be looking at the manuals online. You should be able to figure out how to control things by looking it up. So I understand you're just getting started, but it's important to get in the habit of referring to the manuals. And for some things these days, actually, ChatGPT and other LLMs know basic CompuCell syntax, so you could ask them as well. So for example, if you started out with uniform initializer and you want to switch to BlobInitializer, one way to do it would be to go to Twedit and say you want to change the initializer, and it'll give you a wizard page to do that. Another way to do it would be to edit it by hand. Third way to do it would be to go to the manuals and look up the page that describes BlobInitialize.
Let me see if I can start CompuCell and demonstrate how to use the drop downs. All right, so what I think we'll do next actually is I will just walk through these instructions. All right, so we'll go to new, make a new simulation. And here, smaller. We have our general simulation properties. I'm going to change neighbor order to 2 here, and then we'll click on Blob. And Ramos, I'll show you in a minute how to fix your rectangular slab. You can do another simulation if you want, but you can fix it from the XML as well. So we'll go ahead and hit next. We've got medium. We'll do CellA. Sorry. Not following my own rules here. I put a space in there. CellB. We'll click next. And then from cell properties and behaviors, we need contact and VolumeFlex. We'll hit next. We'll ignore chemical fields. For now, we'll ignore. So this pop-up page essentially lets you specify your values ahead of time. We're just going to leave everything as default for now because we want to mess around with this in the actual XML code ourselves. So we'll click Finish. And what you should get when I open in Player is a blob of cells just kind of wiggling around. Nothing's happening yet. All right, who does not? My color scheme is strange, but it looks like everybody's default color scheme is a little bit different. Not sure entirely why that is, but all right, looks like most people were able to get it. So I think we're set to move on here to the next step. Again, we can always come back. We've got plenty of time. So if you're not to this point yet, don't worry. Just go ahead and grab the slides from online and the instructions are in there. So now we have our aggregate of cells. I'm going to go ahead and stop my simulation. What we want to do now is change our values so that the cells begin to sort, because right now they're all just sitting in place. They're perfectly happy to stay where they are when created. So let's take a look at the XML here of your cell sorting file. So if you go to Twedit, you've got 3 files, xml.python and steppables.python. You'll have one of these for basically every simulation that you build this workshop. There are ways to build simulations in CompuCell that are Python only and don't use the XML, but it's a little bit more complicated, so we're not going to look at a ton of that until week 2 at least. But for each simulation you build, you'll have an XML file, which is your parameter specification file, your base Python file, which is what actually runs, like initiates the run of the simulation, and then your steppables file, which is what controls the changing of values over time and between Monte Carlo steps of the simulation. So we'll take a look at our XML, make sure you can find that. And then there's 2 things we want to highlight here. We have our contact energy and our volume plugins. So these are the 2 things we specified when we walked through the wizard earlier. So you want to look for, in your plugins, you'll have these tags that say plugin name equals. Each of those is its own plugin. So we've got cell type, like we were working with before. You should have 3 cell types, 0, 1, and 2 for medium, CellA, and CellB. We have our volume plugin, which gives us our parameters for our target volume and our volume fluctuation for each cell type. We have a few other things, and then we have our contact plugin. Here is where we specify those interface values between cell types that we were talking about at the beginning. So you'll see here we have medium, medium, medium cell A, medium cell B, CellA, 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 CellB, and CellB, CellB. So one interface value for each, or sorry, one value for each possible interface between the objects. We did have an interesting question going on in the chat in the last session about whether or not changing the medium contact energy affects the simulation. The short answer is it does not really. The medium is continuous and is technically non-spatial. So changing this value doesn't really affect anything, at least not in terms of how your cells behave. And then here we have our steppable type BlobInitializer. So Ramoso, you were asking about how to fix this in the XML. Here you would have, if you chose rectangular, it would be called uniform initializer, and this code would be a little bit different. You can, fix it already using Google. Okay, well, I'll walk through it anyway. It's getting easier and easier to find these answers as you need them, which is good. But what you could do also is we have these drop-down code snippet menus. So we have one for CC3D Python, one for CC3D ML, and one for C++. That's for when you're developing extensions. But if we drop down the CC3D ML file, we've got steppables. We can add, so in this case, I started with Blob initializer. We would add a uniform initializer if we wanted to make a rectangle instead. So if you accidentally picked uniform initializer, you would follow that same process. Just go to steppables, click Blob initializer, and you can delete your uniform initializer. And then you would have your Blob initializer here. All right, so does everybody have these two plugins in their code, the volume and contact? And does it look like what we've got on the screen here? All right, so question. Why do the cells as we specified them here not sort? Why do they all just stay where they are? Yep, so same contact energy terms are all the same. Yes, Nargis. So technically adhesion is introduced already, but like others are saying, the problem, not really problem, but the reason they're not sorting is because all the energies are the same. So there's no difference in affinity between any of the cell types. There's no reason for them to start trying to change their boundaries based on our energy minimization. It's already kind of at the lowest possible energy state. All right, so for our first exercise then, go ahead and run your simulation, which most of you have already done. If you shared a screenshot, you've already done that. We've already gone over this slide. All right, so now the next step is to go ahead and if your simulation is running, go ahead and stop it or pause it, either way. And then let's modify the values in the contact energy plugin to generate the sorting behavior. So I'll give people maybe 3 to 5 minutes to experiment with your starting values in your contact plugin to see if you can create a differential adhesion situation. And so the way you would do this is by modifying an energy value. Something to note here is that your contact energy values must be a floating point number. So they need to be, 10 point something, 5.0, 5.2. It can't be a full integer value. So make sure to keep them as a decimal. And give that a try. Once you've got some movement in your simulation, you can take a screenshot and share it and maybe talk about which values you use. James makes a good point. They can be negative, so they have to be a floating point number, but they can be negative energy values. We have a few people who have engulfment behavior here pretty quick off the bat, but that's an interesting one, Misha. Got a couple people whose simulations are creating kind of this, what you see like with Snigda and Barga, these kind of bands that stretch across the the bulk of the simulation with kind of islands of the other type. Levi, Raghus is good. So Raghu, you'll notice actually has a couple of small bundles of cells that are kind of budding off at the end. Karen, that looks good. Karen's here has a isolated island. If it ran longer, Karen, did that other blue blob eventually reconnect, or is that band of green cells still holding it isolated? Yep, okay, it eventually joined it. Good. Addie, it looks like, so your cells are all separated. Why might that be? And while Addie is answering that, we'll take a look at some more of these. So got some more of the banded marble blob simulations. Okay, so good. So we're starting to get some movement at least. And then, Addie, I might say you might want to look at your, I only change the energy of cells A, A, B, and B, B. And what did you change those energies to? Did you make them higher or lower than 10? Higher, right. So in that case, what is that telling you about what your system prefers? If you could take a guess. So it prefers lower than 10, right? So the lower the energy value, the higher the affinity for contact. So if you've changed all of your cell-cell interactions to a higher number than your cell medium, what's happening is your cells are preferring to touch medium rather than any other type of cell because it attains a lower energy state by maximizing the contact between cells and medium rather than cells and cells, which is why you have your cells kind of all separated there in the middle. So what you might do is try flipping your cell-cell interactions below 10 and maybe differentiating between cell A and cell B a little bit. Does that make sense? Essentially, the higher the energy value, the less that particular interface, wants to happen. Saying that it wants to do this is anthropomorphizing a little bit, but it's kind of hard to talk about it without talking about what the simulation, quote unquote, wants to do to attain a lower energy state. And that's based on, again, the fact that the simulation is allowed to occasionally select for a higher energy value, but it's generally going to trend lower. That's why it creates this kind of sense that it wants to do specific things. All right, so it looks like people have got their cells moving. Yeah, Maisha has an alien face. All right, so if we want to get the values that kind of produce the original video that I showed you in the earlier slides, you can change your values to this. If you've already got a sorting behavior that you're happy with, you can stay there for now because you're going to start messing with them again. But does somebody want to explain very briefly what these contact energy values mean in terms of the simulation? So based on these values, which cell types prefer to touch what other objects? Yeah, B to B is most preferred, A to B is second preferred, everything else is third preference. Yeah, so that's pretty much a good way of summarizing it. The other thing here is that cell A to cell A interactions have the same energy preference as cell A to medium. So for cell A, there's no difference between touching another type of cell A and touching the medium, um, which means that they would prefer or trend towards sorting out on the outside ring. while cell B wants to clump up in the middle and not touch the medium so much. Okay, good. So with that, I think people have working simulations now. Yeah, so this is just reflection questions on the values that we just had. There is this one question, what parameters can you change to speed up the sorting process? So we talked about contact energy. Obviously, you can make some of them super low. Is there another parameter that you might try changing to speed up the simulation? Any guesses? Yeah, we have lambda. Bargo, which lambda do you mean? Yeah, so most people here are saying increase the CPM temperature. So yeah, if you boost the CPM temperature, the fluctuations are larger. Karen, the reason I was harping on your simulation earlier with the kind of isolated island of blue with that one band of green is that sometimes you can end up with the permanently isolated bundles because the fluctuation amplitude is not high enough. But if you increase that, the cells can actually reach out a little bit further with each pixel copy attempt and eventually break through. Um, good. Okay, so next exercise, I give people 10 to 15 minutes here to explore the sorting configurations of contact energy. So we had people with already a variety of different kinds. Can you find a set of contact energy values that approximate each of the following sorting configurations? So we have some people with the engulfed blobs. If you have one type engulfing the other, how would you reverse it so that the second cell type engulfs the first instead? And then can you achieve the side-by-side sorting behavior here? So once you find each configuration, if you've already found one and shared, then that's good. If you can find the others, go ahead and share them in the chat when you land on them, and share your energy values as well. Ellie, yours is pretty close to the side-by-side. My question is, what would you have to alter there to get the cells to stick together more in a circle instead of two isolated blobs? And you can also feel free to share if you find any other interesting configurations. These are just the 4 to try for right now. Okay, Nargis, good. You've got the side-by-side. Obviously, if you're looking for the side-by-side, it won't necessarily be pure left and right. The point is to have a clear line dividing the two, so you've got it there. It's the nature of stochastic simulations. It won't always follow the same alignment. Yeah, Ali, you're very close with the side-by-side. You do have the one or the two red cells on the other end, and then you've got kind of a tight pinch point there in the middle. I wonder if there's something you could modify so that there's a little bit less of a pinch. There'll always be a little bit of one. Maisha, that's good. An interesting symmetrical side-by-side plus blobs. One thing I might suggest, Ali, is if you make your blob initializer a little bit bigger so there's just more cells, and then leave your contact energies where they are, you may notice less of a pinch point effect there. And Barga's blobs are flying away. So let's first ask what would cause individual cells to break off and fly away like that. High contact energy, but high contact energy with what? Yeah, so in this case, if cell A doesn't want to contact itself, so I assume that's what this energy 20 is AA. What's happening here is your cells on the outside, they touch medium and then they realize that they like medium better because the energy is lower than they do like touching their own cells. So you end up with one on the end that's not touching any cell B, and it doesn't want to touch cell A, and instead prefers to touch medium, so it'll actually detach because it wants to be surrounded by medium instead of touching another cell of its own type, if that makes sense. So when they're in the blob, they won't break off and fly away, but when you have them kind of reach an arrangement where one is isolated and only touching B and medium, it'll fly off into the medium. So there's a couple ways you can address that. One would be by making its preference for the medium either equal or higher than um, AA contact. Give people maybe a few more minutes here. If you've already found one and shared in the chat, maybe try another one. And then for the last 30 minutes, we'll have even more extension activities on how to make these simulations even more interesting. So that's good. Yours almost looks like an egg yolk in the middle of an egg. It's so isolated to one side there. Udis has something interesting going on here. It's got side by side, but I'm noticing you're messing with the volume. So what did you change, Udis, to get your side by side pill arrangement like this? While he's answering that, Kyle's got some bands. So Kyle, based on the edges of your cells, it looks like your temperature value might be a little high. That's okay if that's what you were intending. Um, but when you have really wiggly cell boundaries like that, it usually means that the temperature is very high. And I guess you actually have some edge of simulation stuff happening here. Cells bunching up on the boundary. Extremely high. All right, so Yuta says high contact values with medium for both, higher CellA. Yep. Mess with the medium to kill tiny blobs of one color inside the other. Okay, so yeah. Yeah, James, if you're there, Nargues's simulation is kind of an interesting output where the cells have kind of stretched out and grabbed onto the sides of the boundary.
That's a great question. So, and you might say that's actually a bug in CompuCell. What is the contact energy between a cell and the edge of the wall, at the edge of the simulation? Did you define an energy for that? Can you define an energy for it?
No.
So it's zero. And we know that an energy of zero is attractive. And so cells will stick to the edge of the simulation. So if you want to avoid that, you have two choices. You can either use periodic boundary conditions, or you can put a layer of frozen cells as a wall around the edge, and then you can define the energy between that wall and the cells to be repellent. So that's a great observation.
Yeah, so I guess my guess is that your initial blob relative to the lattice size was just large enough that the cells made it over there quickly, whereas other people's might take a very long time to drift to the edges. So we'll talk more about periodic boundaries and how those all work tomorrow, I believe, in Gilberto's sessions. If not, then on Wednesday in Pedro's. It was periodic boundary condition. Oh, so let me take a closer look.
Oh, so if it's periodic boundary conditions, it's simply sticking to itself around the edge.
Yeah. Yeah, in
Just
that case,
around
if
the
it's
edge.
yeah, if it's periodic, you're looking at the same cells reaching from the right into the left side. So that's just all of one cell type sticking to each other. Yeah, in this case, no flux would cause the cells to stick to the wall. All right, good. So we'll go ahead and move on. We'll give people the next set of instructions. There are a number of activities in this slide deck. We don't expect everybody to finish all of them today. Some of them are intended for you to come back to later if you're interested. So for the last 30 minutes, we have a couple of things that you can do. And again, it would be useful if you want to go grab these slides yourself so you can kind of move around between the different activities if you're interested. So for exercise 1.4.3, sorry, this is 1.3.3. Got a few additional modifications now that we've gotten different sorting behaviors figured out. Start messing with different things about the lattice. So what happens when you make each of the following changes? Double the target volume of one of the two cell types. Double the number of cells in the simulation. How does this affect simulation time? Or how does it affect the time to reach equilibrium, which is the point where the cells mostly stop sorting? You have little movement. You'll have to modify your BlobInitializer steppable to do that. One thing you might want to do is try adding a shape constraint to your cells. You can do that using the XML plugins code snippet. And we'll talk more about how to actually make cells of specific shape in tomorrow's sessions. Another thing you can try is how sorting is affected if you change the shape of the lattice from a square to a wide but flat rectangle. There's some hints in the slides here for questions 2 and 4 about how to change those to get those different effects. So if you want to pick two of these, we can look at the shape plugin together in a minute if people are interested. You can try two of these with changing the lattice, changing cell shape. Another option is to add a third cell type to your sorting simulation. There's a couple ways you can do this. You can modify your simulation code directly, or you can start a new simulation with Wizard. An important thing to note is what changes when you move to the 3-cell system, what all you have to update in your files to make it run properly. And then the goal here is to achieve concentric engulfment, where you have one type on the outside with a ring of the other type surrounding the third cell type in the middle. Third option, leaving flatland. So if you were to rebuild the simulation in 3 dimensions, what needs to be changed? You'll notice, obviously, if you're running it in 3D, it will run slower and it will be harder to see the sorting behavior. But if you'd like to try a 3D cell sorting simulation, you can do that. And then we have a stretch exercise here. We had a couple people asking earlier today about tracking individual cells through a simulation. We haven't talked about how to do that yet. But this is in here so that if you want to come back to it later after we have talked about that, you can try this. So if you wanted to say, if we had in an experiment, we wanted a specific cell to see where a specific cell goes, and we wanted to track it over the course of the simulation, how would we do that? So this is something that you will have the tools to do by the end of the workshop, but you don't currently know. So if you wanted to come back around to this later, it's in the slides. So we'll give people, got 25 minutes left. If you want to try to address a few of these activities, I'll leave these on the screen for now. And if you'd like to move ahead to some of the other exercises, you can grab the slides. And then as you find different interesting outputs, please feel free to share them in the chat. If you're not sure why you're getting the outputs you're getting, please share it in the chat with your contact energy values and we can take a look together. Yeah, so we got a comment from 2 about how doubling the target volume results in a faster cell sorting. Was anybody, excuse me, was anybody else trying that one and did they get the same results? Any theories on why that might be? Ramasa says the bigger the volume, the higher the surface contact. That's right. So the larger your cells are, the wider their areas of interface. While people work on these, I will do the shape constraint example. So 2S, how can we adjust the number of cells in the simulation? That's an excellent question. While I've got it open here, So the way that the number of cells is controlled is you have your BlobInitializer in your XML. Am I still screen sharing? Split screen, yes. And what this is basically saying is, so we're at the center, we're creating, we pick where the center of the blob is, which is at 128 by 128 if we have a 256 squared lattice. And then it has a radius of 51 pixels. So it makes a circle of radius 51. Gap means there's space between your cells. Here we have a gap of 0 because we want to create with no cells. And then your width is the width of each cell, the approximate diameter of each cell. So to have more cells, you can decrease your width and increase your radius to create a larger blob, or you can just increase your radius. Let me know if that works for you too. You can also, if you wanted to have an unbalanced amount of cells, and James, you'll have to check me on this, you do cell A twice, cell A, cell A, cell B.
That's right. The one thing is you can't have a space. So you have to
Yeah,
have cell A, comma, cell A, comma, cell B. No spaces.
yeah. And then this would create 2/3 cell A and 1/3 cell B arrangement. You just got concentric engulfment. Yep, that's more or less perfect. Obviously, you don't have to have the individual layers. Given enough time of your simulation, you would probably see that even out. But at that stage, that's a good early concentric engulfment. And you got a very interesting, shockingly symmetrical um, fourfold symmetry thing going on here. Wait, Maisha, I tried the rectangle, and for certain dimensions, there are no cells in view. Could you share your lattice dimensions, your Potts plugin with your lattice dimensions and your BlobInitializer? And then maybe a picture of what you're looking at on your end, what you mean by no cells in view. Yep, there you go. So you probably, your center was outside the actual um, bounds of the lattice. Rasa says, increasing the number of cells helps reach the equilibrium quicker. Why does it feel like the volume keeps on increasing with every step? The volume of the cells, Ramasa? Ah, volume of the entire blob. Um, that's a good question, Maisha. Maisha asked for 3 dimensions. When we say periodic boundaries, is it periodic as a torus or as a sphere for 3 dimensions?
As a torus.
Yeah, torus. Ramasa, what's probably happening as your with lots of cells in the simulation. As the cells relax and reach their target volume, they push out against each other. So it's probably just that your initial state seems more compact, and then as the cells move around and can achieve their target volumes, the whole blob will expand a little bit. And a lot of simulation methodologies, you usually have, especially with simulations that are stochastic, you have what's called a relaxation period, where you create your initial conditions, initialize the simulation, and then let it run for some short amount of time so that your cells reach a more natural state. Um, I used to do molecular dynamics simulations for protein folding, and you would set everything up in perfect arrangement, and you would have to let it run for some fraction of time steps before you began the actual production run to let it assume a more normal configuration. So that very initial simulation that you, or initial step that is in there is usually very tight and constricted because everything is like exactly configured.
There is no Z direction if you only have a thickness of 1.
Yeah, so UDIS there is if you are doing a three-dimensional lattice. In our case, we're doing so CompuCell always runs in 3D, but right now we're just looking at a two-dimensional lattice with a thickness of 1 pixel. And you would need to have at least 2 pixels to have periodicity.
These are
So you can
great
actually,
questions.
yeah, you can actually, if you switch your player to 3D, you can actually see that when you rotate it, we do have one pixel of dimension in the Z, but this is basically like you can think of this maybe as looking at things under a slide under a microscope. And then on the flip side of that, if you're running a simulation in 3D, you can actually look at a slice of it in the XY plane, and you can specify which slice. So basically, if it was in 3D, you would pick XY, and then this number here is how you would move through the cross sections. So you can have something running in 3D and then only look at one dimension or 1 pixel slice of the mass. So Maisha, you got your compacted. Looks like the purple cells met in the middle and then pushed out the blue cells in two directions. So if this is a periodic boundary, what you're actually looking at here is the side-by-side configuration that we were talking about before, because the blue cells are the same. So maybe we've learned that doing the squished lattice is a way to cheat the side-by-side configuration. Okay, good. Was anybody else had anybody tried the three-dimensional exercise? Just building cell sorting in 3D?
It's not bad in 3D. It actually runs faster in 3D than 2D in terms of the number of Monte Carlo steps to sort, because cells move more easily in 3D around each other than they do in 2D. They don't get jammed.
Mhm.
So if you're going to do 3D, you probably want to do a visualization and a 2D section. So you want to, instead of visualizing in 3D, you probably want to render in 2D so you can do a slice through the middle to see what's happening.
Yeah, that's actually a very good point. When we say things take longer to run in 3D, what that usually means is it actually takes longer to render the visual, not so much that the simulation itself takes longer. That obviously depends on exactly what you're simulating, but turns out visualization is the computationally expensive part of most of these simulations, not so much the actual math to move the cells around.
There are a lot of configurations you can have besides pure sorting. You can have partial sorting. You can have a checkerboard, full checkerboard, a partial checkerboard, depending on the energy hierarchies. And if you have 3 cell types, then you can have really a lot of different patterns. To some extent, they look similar, but they're not quite the same if you look carefully.
Addie, are those stuck to the cell wall or is it periodic and poking through the other side? They're stuck to the lattice wall rather, not cell wall. That's interesting. Makes me think of simulating a fried egg. How to optimize your egg frying. All right, good. It looks like everybody is working through some of the exercises. I was working on the length constraint one here. Again, we'll talk more about length constraints tomorrow in Gilberto's cell properties session, and then you can always come back to these later and try them yourself. Yeah, Maisha makes the point. I love how half of us are like, this is art now. Yeah, it's like looking at clouds. We're all interpreting what we're seeing in the cells. But this all gave you a good feeling for what you can maybe start to do with CompuCell. We'll get more into the details of exactly how to make cells do what you want them to do over the next couple of days. To ask, will we learn about generating a lumen in the next lectures?
You can use segmented cells to do that.
The morning session on Friday on compartmental cells, there are methods for building cells with multiple parts that stay together as the cell moves around. O2 did have a question in the chat. When he switches to 3D, he can only see an outline of his cells. Is this the same problem that we were having with that colonic crypt simulation?
Yes, that's a rendering issue. Let me see where. So in 3D, to speed up the rendering, CompuCell only looks at the outer surface of the cells. And then if you take a slice, you sometimes don't see things. So let's see where the setting is for that. So if you go to the CC3D preferences and you go to 3D, the 3D tab, there's a button that says draw outer shell only for faster 3D rendering. Uncheck that. So you go to preferences, which we've used quite a bit. Select the 3D tab. Look down here in the bottom middle of the preferences where it says draw out shell only and uncheck that. See if that fixes it. Okay.
Yeah, Manisha asked, could you go over how to reduce to one cell to start off as in the beginning of the day? Sure. So if you want to have just one cell, the way that you do that is with your uniform initial or with your blob initializer. So let's go ahead and take out this length constraint. Actually, this will be easier just to make a new project. do blob. And then if we go to our XML, the way that you would do this, so what I was describing earlier with the blob is that we're centered at 128 by 128 with a radius of 51 and a cell width of 7. What you would want to do there is just make your radius basically the same size as the width of your cells. So here we would say 4, which would make circular diameter of 8. So if we save and we run this, you'll see we have a single cell. Oh, well, actually you need a cell type if you're going to have cells. So let me put that in. Forgot to specify a cell type. And then let's try that again. Doing my XML wrong. And now CompuCell is struggling. And some live debugging is always a great idea. There we go. So yeah, your initializer just has to be only big enough to contain one cell, essentially. You can do the same thing with rectangular um, initializer. Syntax just a little bit different. Any other questions? All right, yeah,
Somebody asked again how to add a third cell type, I think. Could
Mhm.
you show them how to do it in Twedit?
Yeah,
You can just use the code snippets to do it. So you
yeah,
update the cell type plugin.
yeah. So if we go to, sorry, who is this? Ragu. If you go to CC3D plugins cell type, you'll see cell type module is already defined. Would you like to replace cell type using cell type based definition? Or would you like to comment out the existing code and add new code? So this basically lets you decide if you want to overwrite it or if you want to keep your old settings just in case. I'm just going to go with replace. And then you can actually add this way. And then when you click OK, it'll overwrite your cell type plugin. You can also just manually add the third cell type. Now, the tricky thing is when you do that, you'll have to go through and update your other plugins.
So if we do contact energy, it'll automatically update it, and also the volume, we can replace those. And it'll know that you have a third cell type.
Yeah, so here we can go to contact to replace. You click OK, you'll see that it updates. And volume replace. So you can do it using the code snippets. You can do it by hand. You just have to make sure that you get all the corresponding values in. And so here we would need to add cell C to our types in our BlobInitializer. So the snippets will let you replace code and write code easily, but you do have to know what all needs to be updated. So if you specify a third cell type and then you try to run it and nothing's happening or you get an error, just have to go through and make sure that everything that tracks the cell types is updated. So it's actually, let's see if this runs since we've got it sitting here. Yep. My default colors are awful on my computer right now. I don't know why it picked those.
So one thing, yes, you could change the colors there. Yes.